This time I want to look at the Baxandall bass tone controls. Now there are two forms of this circuit, but I'll start with analysing this form because this is the one that Baxandall originally published. It contains two capacitors, three resistors, and the potentiometer which controls the amount of gain, or attenuation, at low frequencies. As before, we can start to get a feel about how this circuit works by analysing the behaviour of the circuit at both very high and very low frequencies. First of all, consider very high frequencies. Frequencies so high that we can assume that the impedance of the capacitors is negligible compared to the other impedances in the circuit. In other words, the capacitors are behaving effectively just like wires. The circuit then looks like this. The circuit is again based on a non-inverting amplifier configuration, and we have the non-inverting input of the amplifier connected to ground, so as long as the amplifier is in its linear region, the inverting input is going to be held at 0 volts as well. That means the potential on both sides of the potentiometer is going to be 0 volts, the same as the potential here. So no current is going to be flowing through R4 or R2 at all. There is no potential difference across any of these resistors. And if there's no current flowing through them at all, we can effectively ignore them. That means the circuit, in effect, looks like this. And that is just an inverting amplifier with a gain of minus R3 over R1, or minus 1 in this case. So that would give us an amplitude gain of 0 dB. And that's exactly what we want for a bass tone control. It's not affecting the high frequencies at all. All high frequencies are just passing through with a gain of 0 dB, unchanged, apart from being inverted by the amplifier. Now, consider the situation at low frequencies. At low frequencies, we make the opposite assumption about the capacitors. We assume that their complex impedance is very, very large. So large that there is negligible current flowing through them, and we can approximate the circuit just by leaving the capacitors out. That leaves this circuit. And we can simplify this one stage further by noting that no current flows into the inputs of an ideal op-amp, so there will be no current flowing through R4, and therefore no potential difference across R4, so we can replace R4 with a wire. And this would be our approximate circuit at low frequencies. Hopefully, by this stage, you can begin to see how this is going to give us both attenuation and gain at these low frequencies. If we move the slider all the way to this side, the full boost, then the circuit we effectively have is 1K and then 10K plus 1K, or 11K here. Our feedback resistor is 11K, our input resistor is 1K, and the gain we would have here would be minus 11 over 1, or just minus 11. On the other hand, if we move the slider all the way to full cut, then we would effectively have this circuit with the input resistance and the feedback resistance swapped over in value. And that is an inverting amplifier with a gain of minus 1/11. In terms of dBs, that's just under 21 dBs of maximum gain and just under minus 21 dBs of maximum attenuation. If you go through all the algebra to work out what the frequency response of the full circuit is, you should end up with this expression here. It's slightly more complicated than the expression for the treble tone control, because now we have a gain at low frequencies, which is a function of alpha, as well as having alpha affect the position of the zero and the position of the pole. For various values of alpha, we then get this whole set of frequency responses. For alpha equals 1, we have a pole with a lower break frequency than the zero, So our frequency response starts off, hits the pole, starts heading down at 20 dBs per decade until it gets to the zero, and then heads to infinity at a constant value from there. On the other hand, if the zero has a lower break frequency than the pole, then it starts off down here, hits the zero, starts heading up at 20 dBs per decade until it hits the break frequency of the pole, and then flattens off. Or at least that's what the Bode approximation would do. The actual frequency response rounds off those corners in the Bode approximation, and that's what gives this set of curves. There is another form of the Baxandall bass tone control, however, this one. It's somewhat simpler in that it only uses one capacitor, and it's rather simpler to do the analysis as well. It works in a similar way. The approximate circuit at very low frequencies, where you can assume the capacitor has an extremely large impedance and therefore behaves like an open circuit, is exactly the same as the approximate circuit that we saw for the other tone control circuit. And the same is true for very high frequencies. If we assume that the impedance of the capacitor is so small at high frequencies that it effectively behaves like a wire, then this circuit would have a limiting case at high frequencies of this. Now, since the two sides of the potentiometer are tied together by what is in effect a wire, and no current is flowing down here into the op-amp, then there will be no current flowing through the potentiometer at all. So no voltage drop across the potentiometer. The inverting input is always going to be at the value of the voltage on this wire. So once again, we just have the approximate circuit R1, R3, controlling the gain of our inverting op-amp amplifier. And the gain, V out over V in, would just be minus R3 over R1, or in this case, minus 1, or 0 dBs. You can do a similar analysis and end up with this result, and the curves that you get are very similar to the curves from the Type A circuit. Because this is simpler and only uses one capacitor, it's also a cheaper circuit to build, and therefore tends to be quite popular. Next time, we'll have a look at a combined Baxandall treble and bass tone control circuit.